What's up everybody, and welcome to a new video. And in this video we're going to go over my notes for recursion in Python. And here the first note is a definition, namely recursion is when a function calls itself. And then the next note is about some conditions that you need if you want to create a recursive function. So here the first condition is that you need a base case, i.e. a stopping condition. And the second condition is that you need to make a recursive call with some modified input. Okay, so that is what recursion is. So now let's look at an example to see that in action. So therefore I've prepared here this code snippet. So here we simply have a for loop that says for I in range n, and n is equal to 3. And then we simply print out I. So now if I run this, then we get here the result 0, 1, 2. And now let's try to do the same thing here with a recursive function. So therefore let's simply call this function here recursive range. And then the parameters that we're going to need is here the n. And then since we want to print out the I, we also need then an I. So then here, the first part of this recursive function is going to be here the base case. So let's make a comment here and let's call this base case. And now let's think about what that base case should be. So therefore, let's think about what we want to do in this function. Namely, what we do is we print out I, and then we increase I by 1, and then we want to call this function again. And then the next time we do the same thing over. And we're going to keep doing that until I is equal to n. So the base case is then simply if I is equal to n, then we simply want to return. So that is our base case. And now the next condition or the next part is then the recursive call here with some modified input. So let's make also here a comment, and then let's here say recursive part. And here we're going to say else. So if our base case is not true, then we're going to go here on this part of the code. So here the first thing that we want to do is print out I. So let's say here print I. Then we increase I by 1. So we're going to say I plus equals 1. And then lastly, we want to do here our recursive call with the modified input. So here we're going to then call our function again. And then here again, we put in the n. So this stays the same. However, then here we put in our modified I. So then let's do that like this. And this is now our recursive function. And now let's see if this works. So we're going to say recursive range. And then we're going to set the n equal to 3. And the I is going to be 0. So now if I run this, then you can see that we get here the same result as before. So again, we get 0, 1, 2. And if I make this here, for example, 10, then we get here the numbers 0 to 9. And then here, just as a side note, because we are always using here the 0 for our I, we can actually make that the default value. So let's say here I equals 0. And then here in our function call, we don't have to specify here this I. So if I run it like this, then it also works. So this is how recursion works in Python. Okay, so now that we know how recursion generally works, let's look at some more examples to get more experience with it. And here, the first example that we're going to look at is factorial. Namely, the factorial is defined in the following way. So the factorial of n is n times n minus 1 times n minus 2, and then so on until we reach times 2 and times 1. So for example, the factorial of 3 is 3 times 2 times 1, which is 6. And the factorial of 5 is 5 times 4 times 3 times 2 times 1, which is 120. However, there's one special case, namely the factorial of 0 is defined to be 1. Okay, so now let's try to create a recursive function that calculates the factorial of a given number. So let's simply call this function factorial, and the parameter is simply going to be an n. And then here within the function, we again start here with the base case. So let's make a comment for that and say base case. And now let's think about what that base case is. Namely, one base case would be here the 0. So if our function gets here a 0, then we simply want to return a 1. So in that case, then we say here if n is equal to 0, then we want to return a 1. However, that's not the only base case. Namely, we also return a 1 when our function gets here a 1. So therefore then here we're going to also say or if n is equal to 1. Okay, so now let's simply check if that works. So we're going to say factorial of 0. So now let's run this, and here we get a 1. And let's also run here factorial of 1. And then in that case, we also get a 1. So our base case is working. So now let's get to the recursive part. So let's say then here recursive part. Then here we're going to say else. And now here to think about what we're going to put in this part here, let's think about what happens when we put in here a 2, or what we want to happen if we put in a 2. So in that case, what we want to calculate is simply 2 times the factorial of 1. And the factorial of 1 can also be expressed as 2 minus 1. So that is then what we want to return. So let's also put in your return statement. So let's see if that works. So if I run here the factorial of 2, then we get here a 2. And now to make this function here simply generalized to any number, we simply need to replace here this 2 with an n. So if we define it like this, then also our factorial also works here for 2. So now let's calculate here the factorial of 3, which should be 6. So let's run this. And as you can see, we get a 6. And now let's also calculate here the factorial of 5, which should be 120. So let's see if that works. And if I run it, then you can see we also get here a 120. So this is how you can implement a factorial function with recursion. Then the next example is about flattening a nested list. So let's say you are given a list, and then the element within that list can either be an integer or another list. And then the same thing also applies to the another list. And this just keeps going. So to show that, I've prepared here 2 example lists. So this is what these nested lists could look like. And then the goal is to flatten them. So at the end of our function, they should look like this, where we then only have here the numbers and not a nested list anymore. So now let's try to create such a function. So let's call this flatten. And then here we simply pass in our nested list. And then what we want to do is we want to create a flattened list where we then append all of the numbers of this nested list. So we could say here flattened list equals this empty list. However, we can't do it like this, because if we say here flattened list equals an empty list, then in each recursive call of the function here, we're gonna set that flattened list equal to an empty list. So we actually have to put that flattened list into this definition as a parameter. So we're gonna say here flattened list. And now let's think about the actual logic of the function. And therefore let's loop here over list 1 and then print out the elements. So we're going to say for element in list 1, we want to print that element. And then here what we want to do is, in our function, is to loop over the nested list. And then if the element is an integer, then we want to append it to our flattened list. And if it's not an integer, then it's another list. So in that case, then we want to recursively call this function and again loop over the respective list. And then again, we want to, if it's then an integer, then we append it to our flattened list. And if it's another list, then we recursively call the function again. So this is how this function should work. So now let's implement that. So we're going to say here for element in our nested list. And then here we're going to create the base case. So we check if this element is an integer. And if that's the case, we are going to append it to our flattened lists. So we say here if it is instance and then element and then integer. If it's an integer, then we're going to say flattened list dot append that element. Okay, so that's our base case. And now let's get to the recursive part. So here, what we do then is, so if it's not an integer, if this element is not an integer, then we want to, then it's a list, and then we again want to call here this recursive this function. So we're going to say here then flatten, and then we put in the element because that is going to be a list, and then we also put in our flattened list. So this is then the recursive call, and then once we have looped over all the elements of our nested list, then here at the end we simply want to return the flattened list. So we say here return flattened list, and that is now our function. So now let's see if that works. So we're going to say flatten, and then the nested list is going to be list 1, and the flattened list is going to be simply an empty list. So now let's run this, and then here you can see that we now get this flattened list where we only have here numbers 1 to 10. And now let's do also the same thing for list 2. So let's say here list 2, and now if I run this, then you can see we also get a flattened list for that. So our recursive function here is working. And now again, just as a side note, because we are always setting here this flattened list equal to an empty list, we could also then simply create here a default value for that flattened list. So therefore then here, let's say that the flattened list is an empty list. In that case, then we can here delete those flattened lists in those calls. So let's do that. And then let's run the code here again to see if it works. So if you run it for our list 1, then we can see that we get our flattened list. However, if we run it here for our list 2, then you can see that we get those numbers here twice. And this has actually nothing to do with the recursion, but it has something to do with something called mutability. So if you don't know what it is, then I will put a link to the respective video into the video description. But now here, let me just show you how to get around this problem. Namely, instead of setting here this flattened list equal to this default value of an empty list, what we say here is that it should be equal to none. And then within the function, we simply check if the flattened list is none, then we're going to create that empty list. So we're going to say then here flattened list equals an empty list. So now if I run the code like this, then you can see it works for list 1, and it also works again for list 2. Okay, so this is how you can flatten a list with recursion. Then the next example is about a decision tree. Then we can use a decision tree to make a decision based on some given inputs. And to show what I mean by that, I've prepared here these code snippets here. So here we have a decision tree, which is simply a dictionary. And within those dictionaries, then here we have the keys rainy, sunny, and overcast. And the values could be either a string, which would be then the decision, or it could be another dictionary where we then again have here our keys and then the respective values. So that is what the decision tree looks like. And the inputs look like this, where we have here these lists. And for the first inputs here, we only have one element. And for the second inputs here, we have actually then 2 elements. So let's see how this decision tree here should work. So for inputs 1, we have here the input rainy. So therefore then here we look at this key, and then here the value is don't go hiking. So that would be then the decision. And here for inputs 2, we first have overcast. So therefore then here we look at this dictionary. And then here the second element is, or second input is weak wind. So in that case, then we would, the decision would be to go hiking. So now let's create here a recursive function that can do those, or that can make those decisions. So let's call this function simply make decision. And then here we put in our tree and the inputs. And then first what we want to get is here the value of those inputs, which would be then the key of our dictionary. So then here we simply say key equals inputs and then brackets. And then here, for example, for inputs 2, in the first call of this function here, we would need to use here a 0. However, then in the second call of the function, and so in the recursive call, we would need then here a 1. So therefore then we also need here a variable. So let's call this then index, and let's set that equal to 1. And then here we're going to use that index. And here, however, we can't say here index equals 1, because in that case, in each recursive call of the function, we would then again set the index equal to 1. So again, we have to actually use here the index as a parameter in our function definition. Okay, so then when we have the key here from our inputs, we're going to use that key to access here this decision tree. And then the result will be then the decision. So we're going to say here decision equals tree brackets key. And now we can start with the actual logic of the function. And we again start with the base case. And here what we're going to check is the following, namely, if the decision here that we get, if that is a string, then we simply want to return that decision. So we simply say if is instance, and then decision. If that is a string, then we will simply want to return that decision. So let's do that. So return decision. Otherwise, we're going to enter our recursive part. So we're going to say recursive part. And here we're going to do the following. So if it's not a string, then it's again another dictionary. So therefore then we want to call this make decision here, make decision function again. So then what we want to do is we want to return the result of whatever then that recursive function call is. So we're going to say return make decision. And then here as the tree, we're actually going to put in here our decision. So that's the modified part. Then we're going to put in again our input. So we simply pass those through. And then we also need to put in the index, and we also need to change that so that we're going to simply increase by 1. So we're going to say index plus equals 1. And that is now our make decision function. So now let's see if that works. So we're going to say make decision. And then we put in here our decision tree. Then let's start here with inputs 1. And then here for the index, we're going to use or start with simply a 0. So now if I run it like this, then we get the result don't go hiking. So let's check if that's correct. So here inputs 1, we have rainy. If you look at rainy, then it says don't go hiking. So this is working. Now let's do the same thing with inputs 2. So in that case here we had overcast. So we look here at this dictionary and then weak wind. So here the decision should be to go hiking. So let's run this. And as you can see, we get the result go hiking. So that's also working. And now let's also do it for our third inputs. And here we had sunny. So we are looking at this dictionary. And then here we have high temperature. So then the result should be again, don't go hiking. So let's run this. And as you can see, we get don't go hiking. So our function works. And here again, since we are always using here the 0 for the index, we can simply create here a default value for that. So that way we don't have to specify the 0 here in those function calls. So let's delete those. And then let's run those functions here again to see if they still work. So don't go hiking, and don't go hiking, and they still work. So this is how you can then implement using a decision tree to make a decision based on some inputs with the recursion. So with that now, we've covered here all the examples that I wanted to cover. So now let's get to these side notes here. And the first one is about causes for infinite recursion. Namely, the first cause is if you use a wrong base case. And to demonstrate that, let's go back to our recursive range function here. And here the base case was if I equals n. So now let's change that to say if I is smaller than 0. And then here, since we set I equal to 0 and then only here increase it, therefore then I never can be smaller than 0. So therefore then we never execute here this part of the code and we don't return. So therefore then if I define a function like this and then call it, then you can see that we enter here this infinite recursion. And then at some point we get here this recursion error because the maximum recursion depth has been exceeded. So that's the first cause for infinite recursion. The second cause is that if you make a recursive call without modified input. So to demonstrate that, let's also use here this recursive range function. So let's first undo here this base case so that we have our original base case. And now let's see an example for this second cause here. So therefore, let's simply comment out this line here where we increase our I. So we never increase I. So I is going to always stay 0 and therefore never be equal to n. So now if I define the function like this and then here call the function again, then you can see now it only prints out zeros and we again have entered an infinite recursion. And then here again, we get this recursion error where the maximum recursion depth has been exceeded. So those are here the two causes for infinite recursion. Then the next side note states that you can use the debugger to check out how a recursive function is executed step by step. So to demonstrate that, let's use here this Factorial function again. And here then let's set a breakpoint at this line. And then here, instead of calling it with a 5, let's call it with a 3. So in that case, then we get here 6. So now let's here debug this cell. And then here we are currently in the first call of this Factorial function, and n is currently 3. So then here, therefore then this if statement here is not true. So then if I go to the next line, then we get to this one, where we then here call Factorial again. So then if I go to the next line, then you can see now we are in the second Factorial call. So here n is then equal to 2. So again, this if statement is not true. So therefore then we go to this line where we then call Factorial then a third time. So now if I go to the next line, then now we are in the third call of this Factorial function. And here then n is equal to 1. So therefore then here this if statement is true. So if I go then to the next line, we get to this line where we then return a 1. So this third Factorial function here returns then a 1. So now if I go to the next line, then we go back to the second Factorial here, where we were at this line here. And here now, where we called here Factorial for the third time, this returned the 1 as we've just seen. So therefore then, what we calculate here is 2 multiplied with 1. So therefore then, the second function call here is going to return a 2. So then if I go here to the next line, then we are back to the first call of this function. And here, as we've just seen, the second call returned a 2. So therefore then what we calculate here, since n is 3, is 3 times 2. So therefore then we get then here a 6 when we call this function. Okay, so this is then how you can use the debugger to check out how a recursive function is executed step by step. And then the last side note is about a general guideline for when to use recursion. Namely, every task that can be done via recursion can also be done via iteration. And I want to show that by again going through those 3 examples here that we've covered earlier. So let's first here implement this Factorial function, not by using recursion, but instead using iteration. So therefore I've prepared here this code example. So this is what this function now looks like. And if I run it here for our 3, then we also get here a 6. And if I run it, for example, for the 5, then we get here 120. So as you can see, we can also implement this Factorial function here with iteration. So now the next example would be then flattening the nested list. So let's also do that. So therefore I've prepared this code here. So this is what this function looks like when you do it with iteration. So now let's run it here for our both of our 2 lists. So list 1, so that works, and also it works here for list 2. So we can also flatten the list with iteration. And then the last example was the decision tree. So this is a decision tree here. And here let's also implement that with iteration. So I've prepared here this code. So with iteration it looks like this. So then let's run it here for our inputs. So for the first we also get don't go hiking. For the second one we get then go hiking. And for the third one here we also get don't go hiking. So as you can see, you can implement those tasks also with iteration and not just with recursion. So then let's go over these guidelines here for when to use recursion or iteration. So use recursion when the problem is naturally hierarchical or self-similar, i.e. you solve it by solving smaller subproblems of the same type until you hit a base case. And then the guideline for iteration is to use it when the problem is just about repeating a step in sequence. Okay, so this is here this last side note. And with that now we've covered here all these side notes. And with that then we've covered all my notes with respect to recursion in Python. And therefore then we've also covered all my notes now for functions in Python. So we've reached the end of this video. And then in the next video, we will go over my notes for classes in Python. So thanks for watching, and hopefully I will see you in the next video.